transistors are the switches that turn on the ignition coils. So now, in order to diagnose this system, we need to know how to read all of that in the diagram. Let's take a look. Here's the diagram without any color. Can you make sense of it? Now let's add our colors, put it in motion, and then we'll back up and explain how it all works. Now to give you a little visual before we look at this diagram, here's a trainer that has the exact same system on it. So let's see what we've got. A crankshaft sensor that monitors the crankshaft turning, camshaft that monitors the cam, that goes into the PCM. The PCM for the ignition then controls the modules. It's a V6 engine, so we've got the front bank with 3 spark plugs and the module that sits over the top with a harness. And then on the back bank of the engine, we've got 3 coil-on plug spark plugs with the module that sits over the top and the harness for it. So this is the diagram that we're going to be looking at. And here's the diagram before we do any color coding. Now this is a coil-on plug ignition system out of a 99 Olds Intrigue. Now all diagrams have a purpose, and the purpose of this diagram, of course, is for the modules to fire the spark plugs. The front bank has cylinders number 2, 4, and 6, and the back bank has cylinders 5, 3, and 1. We have 2 separate modules, one for the front bank and one for the back bank. Here's where the front module is located, right up front, and then the back module is on the back bank of the engine back here. Each module has its own power source directly from its own fuse. The front bank of the engine has power to all the coils in the module, and the back bank has its own power supply. All the coils have direct power with key on at rest. Now here's this ignition control system. It's all one unit. You've got the module on top, and you've got all 3 coils stacked underneath it. And in between are the transistors. So it's stacked. You've got the module, the control unit, the switches, which are the transistors, and then the coils. Now because it's all stacked, it's very compact. It'd be kind of difficult to illustrate that exactly in the diagram. So keep in mind when you look at this diagram, what they've done is stretch the diagram out so that you can see each of the components of the circuit. Now this is a 6-cylinder engine, and each cylinder acts the same way. But for the purpose of this diagram, I'm going to focus on just one cylinder, cylinder number 2. Here's the number 2 spark plug, and of course we have the number 2 coil that turns on that spark plug. We have the PCM that controls the ignition for 1, 3, and 5, but it also controls it for 6, 4, and 2. So this control here is the output from the PCM. Now that output actually becomes an input for the control module, and that control module then is looking for the switch for the number 2 coil, which is the transistor. So here's all the items to fire the number 2 spark plug. The power comes from the fuse, passes through the coil, and goes to the transistor. Now you know a coil is a single strand of wire wound round and round and round against a solid core. Since it's a single continuous wire, it has continuity. So any power that comes to the coil passes right through the coil, and it goes over to the transistor and stops at an open. The transistor, remember, is the switch. Here are the transistors for the front module, one for each cylinder. Now remember, transistors are closed gates or switches until they're opened. Now remember our illustration about transistors are like faucets, where voltage comes from the source just like water comes from the source. That's what we're illustrating here. Now notice also, this is power to the primary side of the coil and power to the source of the transistor. Terminology is very important, and thus far we've used a lot of terms, but when we talk about transistors, some things now are going to be a little bit different. In a mechanical switch that has moving parts, in an electrical diagram it's illustrated like this, and that is what we call an open. Well, when that switch closes, we call that closed. Now a transistor, remember, has no moving parts, so it can't have a switch like that, so instead it is drawn like this, and this is what we call an open for a transistor. Now we also have a closed, And if you look at that, you'll see it's identical because there's no moving parts, nothing to change as far as the diagram is concerned. We have to understand how the transistor works. Now, an open and a closed is still what we're concerned about. In a mechanical switch, you have current that comes when it reaches an open, it stops flowing, or there's no flow in an open. But in a mechanical switch, when the switch is closed, current can flow. In a transistor, it's just the opposite. When something opens the transistor, the current can flow right through it. But when something closes the transistor, the current comes down and waits at the gate and can't get through until someone opens it. Now this might be a silly illustration, but it does illustrate the point of a gate. If you had cattle in a field, they would be waiting at the gate. They can't get out until someone opens the gate, and then they can get out. Well, voltage waits at the gate. It can't get through that gate until something opens it, and then when it does open it, then it can get through. Back to the diagram. We've got our power. Now let's find the ground. The ground is going to be one common ground. Now, even though each module has its own power, there's only one ground for both modules. So this ground is going to travel up through this splice and be the ground to one module, and then from the splice it will travel over and be the ground to the other module. One ground for both modules. Now the ground wire is a single wire that's wound round and round and round the solid core. So since it's a single wire that's complete, it does have continuity through the coil. So whatever comes to the coil passes through the coil. And it also stops at an open. Now here that open is the gap in the spark plug. Now notice this is the ground to the secondary side of the coil. Here's the same diagram illustrating the primary side of the coil and the secondary side. Both are wires that have continuity that are wound around through it and pass through it. And the same on the ground. It comes to it, wraps around and around through it, and passes through it. Again, back to one of our earlier diagrams, we have power that comes to the primary side and wraps around through it and stops at the gate. And on the ground side, we have our ground wire that circles round and round through the coil, passes right through it, travels down through the spark plug, and stops at the open, which is the gap in the spark plug. We now have power to the primary side of the coil, and we have ground to the secondary side of the coil. But for either side to work, they each must have both power and ground. Remember, this is key on, engine off, at rest. Now the primary power stops at the switch, which is the transistor. We have 3 transistors in the front bank, and we also have 3 transistors in the back bank. Now, we have primary power, but we need primary ground. The primary ground is supplied from within the PCM. It travels up, goes to a splice, so that it can go to the front bank, right to the transistors, and then it also goes to the rear bank, right to the transistors. Now the ground is the same as before. It stops at the switch because the switch is closed. Now for the primary side to fire, it needs to be switched on. That's the job of the PCM. The PCM sends a switched ground signal to the transistor. Now the PCM has the ability to send a signal to each spark plug, each coil, and the number 2 then, the ground would come up and be the input into the PCM and travel right to the transistor. Now when that ground gets to that transistor, the gate opens and current can flow through the coil. So the voltage is down. Now since it has found ground at the transistor, current can flow through the coil. Now remember how transistors work? The power waits at the gate until the gate is opened, and then it can flow through it. Now remember, voltage is consumed by the load, and the coil is the load. So we had voltage coming to the coil. It passed through the coil and went to the transistor and was sitting there waiting for the transistor to open so that the voltage could find ground. When that happened, the load consumed all of that voltage and current can now run. Now, to illustrate a little bit better what's actually happening in this diagram, I'm going to use my old circle board. I'm going to use my power probe, which will show a red light if I'm on the power side of the circuit and a green light if I'm on the ground side of the circuit. Now, the switch is a mechanical switch, and it's what we would call open. In other words, there's no connection between the ground and the power side. So I have power on the power side of the circuit and the load. I go to the other side of the load. I still have power because there's no ground. I follow this down to my switch. I have power on one side of the switch, but there is no connection between ground, which is on this side of the switch, until I close the switch. When I close the switch, my load lights up. The load consumes all of the voltage. So since all of the voltage was consumed, I now have ground on this side, and I now have ground on this side of the circuit. So this is really a voltage drop. All the voltage came to the load consumed all the voltage and dropped to zero. Why do I have ground on this side? Because I still have continuity in the switch. I have closed the switch. So whatever comes to the switch flows through the switch up to the load. Since the load consumed all that voltage, there's nothing on this side of the switch except what's left over, which is the ground. Now, a switch is a switch. This is a mechanical switch. It has moving parts, which we can actually just move. Now, a transistor is a switch, but it has no moving parts. Instead, it has moving electrons. Now, this switch we would call, this is open because there's no connection from ground to power until we close the switch or make a connection. But in a transistor, it's still a switch. It still does the same thing. But in a transistor, we would call this position closed. It's like the gate is closed, nothing inside it can get out until we open the gate. This would be open. Once the gate is open, whatever's inside can get out. So a mechanical switch is open and closed. In a transistor, the gate is closed and open. Think of the transistor as being a gate. The gate is either open, so whatever is inside can get out, or the gate is closed, nothing can get through it. Now, with the gate now open, current flows through the primary side of the coil. If you were looking at this on a lab scope, it would look like this when the coil turns on and current begins to build inside the coil. Now, the secondary side of the coil has ground, but it doesn't have any power yet. That power is going to come from the primary side. Now, when the PCM, which is in control, removes the primary ground, the gate will close, and then no current can flow through that coil. So the PCM removes the primary ground. Now, when that happens, the gate closes, and the current that was flowing through the primary side of the coil can no longer flow because the transistor gate is closed. Now, this primary voltage collapses and travels into the secondary. If you were looking at this on the lab scope, we would have seen the current build in the coil, and then immediately as soon as it was shut off, it turns off. And this is your coil signature pattern. Now, the primary side was able to build voltage, but the secondary cannot hold the voltage, so it immediately collapses and looks for ground. All of that power finds the nearest load, which is the gap in the spark plug. Electricity is so very fast. All of what we just talked about happens in milliseconds. But let's watch it again without any breaks. Again, all of that takes place in milliseconds.